I think we'll find out. I think over the next several years we'll find out if this program rolls forward, and I'm sure we'll learn more, and hopefully they'll develop the plan, you know, and evolve it.
It's going to be hard, man, because the planet's dead.
How do you know that? You're making all these statements.
According to them, the planet's dead.
Okay.
It's not like you can go outside and catch some sun.
Well, the Earth was once, you know, without oxygen too. My son told me about this. You know, I know this is like a really bad digression right away. My son told me this. He said that no, maybe not my son, but somebody told me that, you know, when the Earth was without oxygen, and, you know, the organisms, you know, started to produce oxygen from the ocean, they were producing oxygen so quickly that they basically, you know, oxidized all the iron that was exposed to air, and that's why, you know, we got all the rust, you know, because they're basically one big reservoir of, you know, oxygens, and, you know, all the iron, you know, got oxidized, you know, everything that got exposed was oxidized, and then they were still producing so much oxygen, so that's why they got, you know, I think the oxygen content in air was twice as much as what we have today. So think about, you know, everybody is just you know, putting on an oxygen mask, you know, with a concentrated, you know, oxygen supply, and that's how they got, you know, dragonflies that are like huge, because the breathing apparatus of insects cannot, you know, they cannot deliver enough oxygen for a large insect, and that's why in today's, you know, atmosphere you cannot find, you know, insects that are huge, because they simply cannot exist. They cannot breathe to get enough oxygen to kind of sustain themselves. But at one point of time in Earth's, you know, history, there was enough oxygen in air. The concentration was high enough to sustain, you know, these, you know, humongous, you know, insects.
Well, they said back like in the dinosaur days, like the mosquitoes were like 5 inches long.
So what we need is to send those, you know, we need to send those life forms to Mars first, to basically, you know, terraform and also, you know, produce, you know, oxygen on Mars, assuming they have a way to kind of convert something on Mars into, you know, breathable, you know, oxygen.
Well, they said at one time there was water on the planet.
Mm-hmm. So here comes, you know, the connection to this class. So I got to make a connection, right? Okay. So how do you think computers can be used in this scenario? I can think of at least a few ways, you know, to connect what we just talked about, terraforming Mars and stuff like that, with, you know, computers.
How about the
use
3D,
of computers?
The 3D graphic thing? They can make stuff.
What we can do is start with something very simple. Okay, you know, you can basically model the behavior of microorganisms. Okay, so you basically subject, you know, microorganisms that we can actually find on Earth to an environment that is similar to what we, you know, think Mars surface is like, temperature-wise, air pressure-wise, air composition-wise, and stuff like that. Okay, and then you observe, you know, how they can survive and how they can, you know, kind of interact with that environment. Okay, is that making any sense? And then what do? You collect all that data, right? So what you can also do now is to try to simulate what if we introduce this kind of organism on Mars. Now you have to remember, you cannot just say, oh, you know, we know how much oxygen they can produce, you know, per hour, per day, per year, and whatnot. So in so many years, you know, it's going to be, you know, the Mars will have this much oxygen content. You cannot use that simple, you know, way of predicting the future, because as, you know, these organisms start to change the composition of the air on Mars, so will the temperature, okay, and so will many other things. So how do you take all of these things into consideration? As a person, you know, you cannot. You know, scientists cannot, you know, possibly, you know, look at all these different factors and, you know, just use an equation and derive and say, oh, in 20 years, you know, Mars is going to have, you know, breathable or almost, you know, breathable atmosphere.
In other words, they need a computer.
They need a computer to run
the program.
To run the program, but that kind of program has a special name.
Simulation.
Simulation, exactly. So
simulation is something made up then, right?
Not exactly.
Well, I mean,
made up.
as far as the computer's not.
It's the computer using what we call a model to predict, you know, how things will be
So that would be a theory to us. Then.
It's a theory to us, but you're basically giving it your best shot and say, based on what we know, based on all the experimentation, based on all the data that we have gathered, based on the best theories that we can formulate, and plug in all the raw data, this is what we think the future will be. Yep.
It's like meteorology.
Yeah, and it's getting better. Okay, it's getting better every day. Now, how do we know? I can look at my cell phone right now and kind of know. Okay, how will temperature fluctuate today? What will be the temperature at 1 o'clock today, 1 p.m.? Okay. Now, you guys all have looked it up. I mean, you can go to weather.com and look for an hourly weather change or weather prediction, and I think it's getting better. Okay, the prediction is definitely getting better, day by day, year by year. Whereas before they can do like a rough estimate of tomorrow, but now they can do it like based on hours. You can actually predict tomorrow at noontime what will be the temperature, and it's fairly accurate too for the most part. So these are all based on simulation. You plug in all the equations, you plug in all the theory, and then you just let it run. Now, obviously, you cannot do it into the very far future because there's still a lot of stuff that we cannot predict, but it's getting better. So and that's how you can tie in that story of how to terraform Mars to back to computers. Is that making any sense so far? Okay. How much computation power are we talking about? We'll just run it on a few i7 processors and it'll be done in a few minutes. No. What type of processing power are we talking about? Massive. Okay, we're talking about massive amount of processing power. Who has, what do you think those processing power come from?
Satellites.
No, not exactly satellites.
Let's say there's people there now, they're experimenting and they're staying there now. Well, that'd be the only way they can communicate, right? The satellite.
Satellite?
How would they communicate from the planet to us?
No. I'm talking about processing power to do the simulation, to do all the calculations.
Wouldn't you? I know, but wouldn't you use a computer to communicate though? With them?
You mean people on Mars?
Yeah.
No, we are not even close to sending people to Mars. I'm talking about.
I know that, but they're already working on the process. I'm saying, say that there are people there now. How would they communicate through computer or satellite?
But I'm not talking about that. I'm talking about how do you run the simulation so that you can say it's even feasible to put people on Mars and they can self-sustain. So I'm talking about that. Okay, so let's look up the fastest computer in the world. And this is always changing too. The interesting part is this is always changing. Supercomputer may have the top 500 list. Okay, so this is just last year. In year 2012, Cray Titan was the fastest computer, and its computation speed maximum is 17.59 p-flops. Okay, what do you think is a p-flop? If I don't hover my pointer over p-flops or look it up, now the P stands for peta, P-E-T-A, which is a measurement unit. What is 1 peta?
10 to the 15.
10 to the power 15, yes.
Okay.
So this is 10 to the power 15 floating point. FL is floating point. OP is operation. O is operations. P is per, and then S is second. So every second they can make basically 18 times 10 to the power of 15 floating point calculations per second. That many calculations. That's on a per second basis.
So what would that be?
Huh? What was your question?
What would that be?
That's a lot of calculations. Okay, a floating point calculation is one that you need when you need to do sine, cosine, square, and stuff like that.
So
in
you're talking
simulation, what?
Talking millions?
No, we're talking about 10 to the power of 15.
I don't know what that is. That's why I asked what it was.
Well, let's look at it. Okay, let me just write that number out. So we're talking about 18 times 1000. That's 1, 2, 3, 4, 5.
Hey,
This many floating point calculations per second.
that's a lot.
That is a lot. What is a million? This is a million. This is 1 million million. This is basically 18,000 million calculations per second.
That's a lot.
Okay, that's basically what the fastest computer last year can do. And you can probably expect, because the supercomputers also follow Moore's law, so this is also doubling every 18 months.
Between 2010 and 2011, 8 flops were added.
Yeah, that's pretty much following the curve. Oh, it's actually faster than that curve too. Yeah, it's a little bit faster than the curve. So you can expect, at this point, it's probably already 20 something. 20 times,
Wow.
1,000 times a million times a million. Yep.
With that kind of processing power and speed, other than simulations, what else would it be good for?
Breaking encryption. That would be a pretty good use of all that computation power. Yep.
Sequencing a human genome.
Sequencing the human genome, that's done already, isn't it?
Well, they're already doing that with PS3s.
What they found about the human genome was, your genome is not the only factor controlling, how, biologically speaking, how you become, because they also found that, depending on how things are folded, there are basically super genome structures that can also determine, how people grow up to become. Because they did experiments on twins, and you can have a pair of twins, basically in terms of the genome are identical, but they can grow up to be entirely different. There was, a Nova episode on just that topic. So they just found out that, what we thought basically determined, how people would become, at least, just biologically speaking, was not really as simple as they thought it would be. And now it requires even more computation power to also, take those other external factors into consideration. So we always have use of computation power.
So the Cray Titan can simulate how a person might grow up.
They can at least, try to figure out, how
Or
the
see if they
different
can do
factors
life on Mars.
interplay. Sorry?
Or see if you can do life on Mars.
Or you can see, how feasible it is to, terraform Mars using microorganisms of some kind. So this is really interesting. I mean, this is interesting. And how do you think that computer will be placed? Where do you think we'll find a facility for this kind of computer? How big is the facility, and what would be something that's special about that facility?
It'd have to be cool.
So it's not something they can put under your desk.
No.
A lot of power.
Research labs.
Mm-hmm.
Have a really big electric bill.
A really huge electric bill. And what is the limiting factor now? I think we talked about that once, and that ties into what we were talking about last Thursday directly too. What do you think is limiting? This is called a data center, okay? It's a very big, huge, data center. Go ahead.
Power supply.
Power supply. Well, that turns out not to be the main issue. Now think about it, okay? Let's think that power supply is not an issue. Okay, you have an on-site nuclear plant supplying power to this supercomputer. So that's not an issue. What is the issue? Go ahead. Heat, exactly. Heat dissipation turned out to be the largest limiting factor today. In other words, you can pack a lot of electronics into a room, okay? No problem. We can run tons of cables to bring power in. We can have a nuclear plant right next door. And that's partially why Google also became a certified power supply company. They can actually legally, they're licensed to generate power and put it on the grid now. Okay, and that's because I think they have a long-term plan to become their own power supplier, because their data centers were consuming so much power. It just makes sense to be having quote unquote in-house, okay, which is basically another building right next door generating all that power. Okay, so it's not an issue. You can have a power plant right next to your data center. Power is not an issue. As it turns out, it's how much heat you can extract. That is the limiting factor. How do you get heat out of a computer? Well, let's take a look at how we do things, in a Newegg way. Okay, So I think we looked this up, or we at least mentioned this, last Thursday. So we go to take a look at.
So the
fans and heat sinks.
supercomputers, would they need like giant fans or air conditioner?
It's
type?
not going to be air cooled. Okay, so you're talking about air cooling, okay, which is the last stage. Okay, everything has to be cooled off by air, at some point, or they can be evaporative or stuff like that. Let me just kind of look this up first, and we'll look at CPU fans and heat sinks. And these are the typical heat sink or fan that you would put into a computer. I picked one that was just okay. Let's do it by best rating. I picked this one for my own setup. It's not expensive if you compare the price of this item to all the other ones. $30 for a heat sink is basically the cheapest within the first 6 items. And it has 4,038 reviews, and it has 5-star out of 5 or 5X out of 5. So it's a very reasonable product for the price. Okay, it may not serve gamers or people who want extreme processing power, but I think for the average person, yep.
That's actually one of the highest recommended for gamers
Even for gamers. So it's not just for like typical average application. It's all for gamers even. But that is not even close to the kind of heat sink that you need for the supercomputer that we were talking about. Yep.
Liquid nitrogen?
Liquid nitrogen, some sort of, it's not really just liquid nitrogen, because what do you do with liquid nitrogen once it becomes gas, right? Because you remove heat from phase change, okay? Phase change, not phase change, but it's PHASE, phase change, okay? Which means you're going from liquid to gas, okay? And that phase change, basically removes, energy or in the form of heat, okay? So what do you do with all that nitrogen that is now in gaseous state? You have a big pipe, okay? It goes all the way to some exterior part of the building, and it has to be compressed again. And the compression itself, will cause the heat to basically get radiated into air, and then it becomes liquid again, and it can come back and repeat the whole process again. Okay, this is just completely air cooled. So what we are talking about the difference between just air cooling versus using liquid to help bring all that heat away is between a Volkswagen air-cooled engine from the 60s to a modern engine that uses coolant. Which one is more efficient at removing heat? With coolant, right? Because how many cars produced today, mass produced today, uses air cooling? How many cars have that kind of engine, gas engine? Even electric motors use coolant. Okay, if you look at all the electric cars, okay, they are not air cooled, because air cooling just doesn't have enough efficiency to extract all the heat. So with supercomputers, it is the same thing. The limiting factor is how much heat can you extract out of a certain area or certain size of volume, without causing the whole thing to overheat, or because extracting heat takes energy for one thing, and two, it also takes a lot of surface area, because everything has to be dumped into the atmosphere at some point. Okay, and that's the limiting factor. Now that also kind of brings up another interesting question. What type of processor do you think this kind of processing center has?
Custom built processor.
They're kind of custom built.
I think
Mhm.
I think the latest supercomputers are actually using high parallel processing, like video cards, because a lot of them use. I think they're using the Kepler that NVIDIA made. They were putting a bunch of those together and making supercomputers with them.
Yep. So right here, Titan has AMD Operon, which is a i386 type processor combined with an NVIDIA Tesla GPU or graphics processing unit to improve energy efficiency. And that's because your graphics card actually has more processing power per energy used compared to your main processor. So in this kind of setting, the main process is nothing more than a foreman, a supervisor, to dish out all the work to be done. But the workers are basically the Tesla GPUs, the graphics processing units, that is actually doing the bulk of the processing. Okay. So are there any questions about this? Look at the power this thing is using. What do you think this means?
Megawatt.
Megawatts, 8.2 megawatts. What is 1 mega?
Million.
1 million. So this thing is consuming close to 10 million watts in terms of power consumption. Yep.
You said the heat has to be observed. How can they not put that location in Alaska, which is very cold?
In Alaska?
Yeah.
Because the data communication is another problem with some of these, data processing centers. So it does make sense, but even in Alaska, there's a season change, right? And then you have to transport, your entire research facility, to go along with it. Now, most of the time, people who use these supercomputers can remote in, can telnet or SSH in. Basically, they can run these programs remotely. They don't have to be on-site. But you still need on-site staff and people to maintain the computer. Which also means they need to have a way to transport materials, supplies, repair parts, and whatnot into the data processing center. And if this is located in Alaska, and you run out of hard drives, that processing center will have to shut down until you have enough. You have the next batch of hard drives shipped in. Yep.
For a sense of scale of that, it seems like a big number, but power-wise, it's really not. One, the small dam down at Nimbus, one of the generating units there makes about 8 megawatts. So that small drop from Nimbus Dam down to the American River.
Yep.
And at Folsom Dam, those units are about 70 megawatts. So
okay, but we are thinking
the size of that machine to power that is it's not all that big. The power is not really a factor for getting that much power.
Exactly, but it's the extraction of heat that is the problem. Because most of the power that you put into a computer, what is it converted into? You cannot destroy energy, okay? Well, we don't know of a way yet to destroy energy. You cannot create energy out of nothing. So what we are really doing is converting energy from one form to another, okay? Everything that you know of, okay? Well, except for quantum scientists and stuff like that, okay? But everything that we can see and touch and feel and experience are basically just converting energy from one form to another. Your lights, okay, right here, is converting electrical energy into light or photons, and also heat. And that's why when you feel light bulbs, even fluorescent tubes, they're slightly warm because that's also a form of energy. What about your car? Isn't your car generating energy when you step on the gas pedal? No, it's just converting it. It's converting it from chemical energy, which is stored in gasoline, into and oxygen, into mechanical and heat energy. So we are just converting energy from one form to another. Is that okay so far? Okay, you cannot destroy or create energy. Okay, whatever we have is whatever we have, but you can change its form. When you run a computer, regular computer like this, or your cell phone, or your tablet, or your laptop computer, you know that it starts with electrical energy, right? Or chemical in the case of a battery. But eventually it gets converted into electrical energy. And then into what? Mostly. Well, into computer processing power, right? I mean, all the energy is converting into all the electrons doing all the logic work, doing all the calculations and whatnot. No, that's not really the case. What do you think most of the energy converts into? Heat, exactly. Okay, so if your computer is consuming 75 watts, because you can buy those little meters from Fry's and other places, so you can actually monitor the amount of energy used by a computer or whatever appliance. A typical computer would consume, a desktop would consume maybe 45 to 75 watts. I know because I did the measurements. Yes, you would figure that somebody would do the measurements, and I did. Just so I can figure out, how long my UPS, my interruptible power supply would last. Okay, so 45 to 75 watts, and almost every single watt of those energies got converted into heat. Okay, so when you run a computer that's, let's say 200 watts, with a gaming computer, 200 watts is nothing. When you're actually actively playing, games, I would say 500, 600 watts would be typical on the average.
for single video card about 400 or 500.
Yeah, but
It's
if you
more
have
like this.
two that are linked, so you're looking at easily 600 to 700 watts, and so you basically have a 700 watt heater in your room when you're playing your games. Yep.
The add-ons to multiple computers or laptops playing games at the same time that will use electricity at the same time as well. That adds up quite a lot.
Okay. So in that case, you run into the same problem as these supercomputer processing centers. You have a problem of extracting heat from your room. Think of a LAN party where everybody brings in these super gaming computers, and you stuff everybody into a 12 by 12 foot room with 4 or 5 of these computers running at the same time. No, he's already screaming, no! You're gonna kill the computers and then the gamers, right?
Yeah.
Yeah, because you cannot extract the heat fast enough, even in the winter, because that will warm up the room real fast. Okay, each computer is 700 watts. You have 4 of those. You have 2,800 watts. Okay, a regular heater, a space heater, is only about 1,500 watts. So you're basically saying, I have 2 full electric heater running in the room. First of all, can your breaker handle it? It's gonna pop the breaker first. Okay. Now, if you specially wire the house so you have a LAN party room, okay, let's just say that you do have that kind of room. Okay. The next problem is now you have 2,800 watts of heat generating in that room, not even counting the people, because each person easily accounts for at least 200 or 300 watts of thermal output. Okay, so you're talking about 4 kilowatts of power in that room by itself. Okay. Okay. I cannot do the conversion into BTU. I'm pretty sure someone who used to work in the HVAC industry can easily just mentally figure out, oh, you need this kind of size of compressor just to get rid of that kind of heat. Okay, and this is only one room, 12 by 12. Yeah, and the data processing center has exactly the same problem. Okay, they just cannot extract enough heat quickly enough, because as you said, 10 megawatts is nothing. A small dam, hydroelectric generator can easily, generate this much energy. The question is, okay, if you just think about it, like the Nimbus Dam, how did that water get up, with a height differential to begin with, in order to generate that kind of energy by flowing through the turbine when the water falls? How does water get up? I mean, things usually just go downhill when you let them go by themselves. So how do we get water from a lower energy state to a higher energy state because they're now higher? Rain, evaporation, and rain, right? How much energy do you think it will take to boil water from a lower part of a dam so that the water will go back up to the higher portion, condense, and so you can basically have that water to fall back down again? Lots of energy, okay? And that's what we are talking about here. 8.2 megawatts is not a whole lot when it comes to generation, but when it comes to having 8.2 megawatts of heat to get rid of, that's a lot of stuff, a lot of heat to dump into atmosphere. Is that making sense so far? Okay. So that's the kind of limitations that we are running into in terms of how much processing power can we pack into a small building. And somebody mentioned, what are we going to do with all this processing power? When was the last time you saw a movie that was mostly, if not completely, done by CGI, computer-generated graphics? Which movie did not have any component of CGI?
Evil Dead?
Huh?
The Evil Dead movie was mostly actually practical effects.
Wow.
Yeah, that was actually one of the #1 thing that they
tout.
Yeah, they were like, absolutely no CGI, practical effects the whole way, like the original.
Wow. Okay, but very few.
Yeah.
Very, very few. Especially with sci-fi movies, they have a lot of stuff that is actually computer generated. If you look at companies like Pixar, okay, what do you think Pixar can do with a fast processor or fast computer like the Titan? they can release movies a little bit faster. Okay, the rendering of an animation like that you watch, from Pixar actually takes quite a bit of time to render. Okay, it's not really as simple as you might think. Okay, I think we talked about this last time too. Do you guys still remember when we talked about gaming last Thursday? Yep, go ahead.
Well, actually, one of my friend's parents, she audited DreamWorks.
Okay.
Because they were trying to file a simulation, like we were talking about earlier, a model that they developed of tornadoes that was the most accurate to date as a scientific research on their taxes rather than entertainment, because they developed that model for some scene in, I want to say a Shrek movie or something.
Okay.
But it was the most accurate tornado model that they'd ever had, and they generated it using a supercomputer.
Yep. But it takes a lot of time, it takes a lot of actual computer time to simulate, just a few seconds of actual real time. And that's why, with more processing power, there's always, something to use it up. It's like there's not enough processing power ever. Okay. Are there any questions so far about, all these, discussion? Yep.
Well, what do you think about the U.S. the Air Force's supercomputer that they built out of PS3s?
I think by today's standard, that probably it's a dinosaur. At the time, it was innovative. At the time, it was innovative because it doesn't have a lot of cost, because it's using just off-the-shelf parts for the most part. It's making good use of processing power, and it doesn't have a lot of thermal power dissipation. But I think by today's standard, using Moore's law, how long was that ago? At least 3 or 4 years, right? So we are looking at 1/4 of what they can also purchase at this point. And I'm pretty sure they're staying away from Sony now.
I think it was called a Condor cluster.
Okay.
Yeah.
And cluster computing is one of the things, or one of the ways that you can actually combine the processing power of multiple computers, and basically end up with a lot of processing power. And we can do it in the computer lab. Just go to the computer lab, run a particular version of Linux that has clustering built into it. Then you can basically treat the entire cluster as if it is just one single computer and say, run this program. And there are special tools to distribute all that processing power to different computers.
Well, if you said it was made using PS3s.
Yeah, the Condor cluster.
Well, the PS3 itself is 7 years old, and the processor in the PS3 was under development 2 years before the PS3 was even released. So it's actually a 9-year-old processor that it would be using, but in a cluster, you said.
That cell processor of the PS3 is pretty watered down so that people could afford it. The real thing is just blow the PS3 out of the
You can probably know how old it is just by looking at the process. In other words, look at the size of the transistor. Okay, I will bet you it's probably close to 90, if not more, nanometers, in that processor. It's now down to 22. Okay,
I think it's 120-ish.
120-ish. Yeah, so we are now down to 20. 22 is the ongoing in production Pentium processor transistor size. And that's a really good gauge of what is the age of the design. Just look at the process that it uses. Okay. All right. Very good. Okay, so we look at these processors, or processor coolers. So let's take a look at this one. Newer version available. Oh man, I bought it before the new version was available. All right.
I apologize.
Okay, so when you look at the size of this thing, when you look at this picture, it doesn't seem that it's big or anything. It's 120 millimeter square. This is what you're looking at, okay? 120 millimeter, which is about what, how many? Which is about what, 4 to 5 inches? I would say about 5 inches or so. So you're looking at 5 inches by 5 inches.
Not that big.
Yeah, that's about 5 inches. So 5 inches by 5 inches, square is the size of the fan. Okay, but if you look at the side view, it's kind of tall too. Okay, so if you look at this design, it took these people, or people who make processor fan, heat sinks and coolers, it took them kind of many years to kind of perfect the technology to make it inexpensive and yet effective at the same time. Okay, so let's take a closer look at this thing here and kind of name the different parts so that we can actually tell how it can get the job done. You can tell the silhouette of the fan. That's basically just making the air flow to extract the heat. The bottom part here, let me see if they don't have a picture of the bottom part.
Right there, I think, on the middle, on the bottom. You can sort of see it.
Oh, it's flipped upside down. Okay, thank you. Okay, so the bottom part, which is what we see as the top here, this is the bottom part. This is the part that will be in contact with the top of the processor core itself, which is not actually touching the silicon, it's just touching a metallic part that is fused to the silicon. That part is an aluminum block. You can tell from the color that it is an aluminum block. Aluminum and copper were the best material for conducting heat, unless you want to spend a lot more money for gold and silver and all the other precious metal. Okay, I think gold is still the best, for heat conduction, but it's also very expensive. Okay, and you have all these pipes, going into the fan. If I, flip to the other direction, we have all these copper pipes going into the fan and basically attached to the fins. Okay, what do you think is inside the copper pipes? Do you think it is a solid copper pipe, or do you think it is a hollow copper pipe?
Hollow.
It's hollow. Okay, so if it's a hollow copper pipe, how can it transport heat effectively? What is inside that pipe? Glycol or some kind of low boiling point liquid. Okay, so what you have here, it's called a heat pipe, by the way. Okay, these copper pipes has a special name. It's called a heat pipe. Many years ago, I go to these trade shows because I used to work for a semiconductor company. They claimed that they were at the leading edge of technology, but I would call that the bruising edge of technology as opposed to the cutting edge of technology. But anyway, I get to go to these trade shows, and it's always entertaining. So they had this experiment. So they give you a little pipe like that, a copper pipe, about the size of a chopstick. Okay, about the same thickness and about the same length as a regular chopstick. You go to a Chinese restaurant, you get a chopstick, and they have hot coffee or some kind of hot liquid in a cup. So they will ask you to hold on to the little chopstick like heat pipe and dip it into the hot liquid. In a fraction of a second, okay, not even a whole second, you have to let go of the heat pipe. That's how fast you can conduct heat. Okay, so the question is, how can they get something done, or how can they transport heat so effectively when it's hollow? It's not even solid copper. And when you look at the inside of a heat pipe, it looks like this. Okay, so it's basically a sealed pipe that is made out of copper on the outside. On the inside, it is textured. Okay, it has some kind of texturing to increase the surface area of the inside. So you have some kind of texturing in the inside, and then it has some kind of liquid, as you said. Okay, a low boiling point liquid. So what happens is you have a very small amount of liquid maybe here, and the surrounding is hot. Okay, so let's say this is just hot coffee, not even boiling water. And what happens is all this heat is going to make this water or this liquid evaporate. When it evaporates, once again, it's called a phase change. It is changing from liquid state to gas state, and it takes all the heat away from it. And all this stuff will go all the way up to the cooler part of the heat pipe, where the surface will be cool enough where it can then condense back into a liquid state. And then the liquid will just kind of go back and forth between the gas state and the liquid state, and basically distribute heat very effectively using this mechanism. And that's basically what we have here in that picture. All the copper pipes, quote unquote pipes, they're all heat pipes. And they can very effectively transport heat from here all the way throughout the entire fin. And then you have your fan, which we can see more clearly with a side view. This is a side view. This is the 120 millimeter fan. And the fan just moves air through the fins in order to cool down the fins, and then the fins would in return cool down the heat pipes and then the heat pipes in return will cool down the processor. And that's how the a modern processor cooler or an air-cooled cooler works. And this one works very effectively. And do you guys remember what I talked about last time? That I encountered one kind of hiccup or minor issue with this particular cooler.
I can tell you an issue I had with it.
Yep, go ahead.
My case isn't wide enough, and the top right there actually hits the side of my case.
Yes.
That's
In my
the issue
case,
I
my
had.
case was tall enough. I have a case that it has enough width to it. But I have a CPU tray, and with the CPU tray, there's a overhand, minimum clearance. It would not clear it.
I had to cut mine out.
I didn't cut it. I just took it apart and put it back on again after the motherboard cleared the clearance problem. But basically, this is a very tall CPU cooler, so you really need to have a big case to fit something like that in. But it does work effectively because it does move air very effectively. And most of the time, the processor on the motherboard is close to one side or the exhaust side of a case. So it just kind of works out, and gets rid of heat very, very, very effectively. Are there any questions about all this stuff that we were talking about? No questions? All right.
Roll sheet?
The roll sheet dissolved in my case because I got water in it, so there's no roll sheet today. And you can also see the prices, of a CPU cooler. Range from $30 to $80 to $84 and up. Okay? I mean, you can buy very expensive, CPU coolers, and yet, the one that is the least expensive out of this entire page is also the most highly rated particular one. Yep.
That was actually, I think it just recently went down because of the new model maybe.
Oh, okay.
But back when I bought it, it was $70.
It was?
Yeah.
Okay, so I kind of lucked out. Because I bought this, it was more effective than my other CPU cooler that I bought with my cisc310, which is kind of cool. There's one thing that you have to, let's go back and take a look at the pictures again. Okay. This is the surface that will be, that will be placed next to the processor or the top of the processor. So the question is, what do? We talked about this already. I just kind of want to make sure that you guys remember. Do you just kind of slap the CPU cooler on top of the processor? Make sure the surface is as clean as possible so you don't have anything in between the surface of the CPU cooler and the top of the processor. Is that how we do things, or no? What do we do?
You need to put thermal paste in between
Yep.
to fill in all the small imperfections and to
Yep, exactly.
better contact.
But why do we need that? I mean, it seems like putting anything in between will make it less efficient at getting rid of heat. So why do we want to put something in between? Well, let's take a look at the microscopic view between two metallic surfaces. Okay, you look at the top, the bottom of this thing. It looks pretty flat. I mean, it's almost like perfect, right? And let me see if I can find a picture of an i7 processor. Pretty sure I can find something just by using Google. Right there. I mean, this is a really, really typical picture of an i7 processor. Just from the picture, I cannot tell whether this is a socket 1155 or a 2000 something pin socket type. Some of you who have assembled many, many different computers can probably just tell right away. But that's not even the point here. The top of this whole thing is a metallic surface, which looks kind of flat. Okay. So the question now is, if you just put the heat sink, the flat surface of a heat sink, which is the bottom of a heat sink, on top of this thing, that should make pretty good contact, right? No. That's not actually true, okay? Because when you look at the actual surface or the contact between two so-called flat surface, it's not really that flat, okay? In other words, when you look at a microscopic view between what we see in the picture as a flat surface, It's actually textured. Okay, there's a lot of stuff going on, and if you look at the other surface, it's also the same way. I mean, it's really textured. So what you're looking at in terms of actual physical contact, when you put a heat sink directly on top of a processor, you're looking at one point of contact here, maybe one point of contact here, one here, one here. The rest of the two surfaces are not contacting at all. And that means you can spend hundreds of dollars on an expensive CPU cooler, but if this is the kind of contact they're making, it doesn't matter. Your processor will shut down by itself because it's going to be overheating, and you're not going to get anything out of it. And this is why we have the concept of thermal paste. So thermal paste, if I use another color here, blue, is basically filling in all the gap here. Okay. All right. So what is going to happen with these gaps? Well, the gaps are now filled in using what we call thermal paste. But how is that going to help in terms of dissipating heat? Why is it helping? Because when you look at thermal paste at room temperature, it's kind of thick and kind of gooey, right? I mean, you would never think that something like that can possibly help in terms of helping one surface, which is the bottom here, to transfer all that heat to the upper surface. Let's take a look at a much smaller proportion here, and we have a kind of not so regular surface on one side and another not so regular surface on the other side, and then we got thermal paste in between. Okay, so all this stuff here is thermal paste. Okay, what do you think is happening between the hot surface, which is the bottom one, and the surface that is supposed to extract all the heat away, which is the top one? What do you think is happening in between? What is happening to the thermal paste when it is warmed up, when the bottom one is starting to heat up? It's not gooey anymore, for one thing. In fact, what happens is a lot of times it starts to circulate. It moves. It's like lava lamp. Okay, it starts to move. It's actually removing the heat sometimes by actual movement, microscopic movement of the paste. Now this paste here, if you use what we call, do you still remember the brand name that I was referring to, the model name last time? Arctic Silver 5. Okay, so what it does is it has microscopic actual silver particles inside here to make up the bulk of the paste, and silver is also a very effective metal for transferring heat, for conducting heat. And that's why thermal paste is so important. If you go for the cheap ones, it doesn't do it as good of a job. And then when we went to the website last time, we found out that they have a ceramic type that has a number of 2, which means the thermal resistance is probably 1/2 of the Arctic Silver 5. Okay, which also improves the efficiency of transferring heat from one side to the other side. Are we doing okay so far?
So you're saying ceramic actually is a better conductor of heat, or is silver still the best?
Correct. According to that website, that's basically what they are talking about. I think the ceramic that they're talking about is not the typical ceramic that you get from like a pottery class or something like that. I think that is specially engineered to become a part of a thermal paste to improve the thermal conductivity of the paste. So we are looking at a very engineered product and not really just your typical ground up ceramic particles.
All right.
So the shape of it may have a lot of surface area, and then the material itself may have metallic stuff already infused to improve its thermal conductivity.
So it's basically it's a silver and ceramic.
I have no idea what the actual material is made out of, but ceramic is just a generic name for that type of material. But when you look at the engineering of ceramic, it can range. It can go from one range to another range.
Okay.
Yep.
The ceramic is like the one that some people use to straight, that kind of ceramic.
Well, let's look at the word ceramic.
Conductor.
Ceramic is really just referring to a general class of material, which is a composite, and it is also It's an inorganic, non-metallic solid prepared by action of heat and subsequent cooling. It has a crystalline or partial crystalline structure. I think that's really the most common property of ceramic is it breaks easily. Okay, it's because of it has a crystalline, structure. But the crystalline structure in this particular case can also help conduct heat. I have no idea how they engineered that type of ceramic to use in the thermal paste, but according to that particular website, it has a better thermal conductivity than even Arctic silver. So when you look up Arctic silver, the next generation of cool. Let me see if they have any explanation of the product. Trilinear ceramic content. Okay, it's a composite of aluminum oxide, zinc oxide, boron nitride to allow the thinnest possible bond line between modern processors. Critically sized particles and now ultra high shear mixing technique maximizes the thermal performance and help maintain a stable, homogeneous suspension. So it has to do with the size of the particles, how they actually engineer the product to make the particle size, really well controlled. Which is kind of interesting because, this is all material science. It's not electronics, but this is how material science can directly impact, the application of electronics. And it has a polysynthetic suspension fluid, which is the kind of the gooey stuff, the substrate of the entire thing. This is polysynthetic, which means it is synthesized to make sure that it has a very consistent, thick viscosity, and they also know exactly how it will perform under different types of temperature. It's not unlike synthetic motor oil versus dyno motor oil. Which one is better? You can just look at the price and know which one is better, right? So why do you think synthetic motor oil is better? I know I'm digressing.
It doesn't break away.
It doesn't break down as quickly, and also it has a much more consistent particle size compared to dyno oil. Okay, it's the same thing here. Everything is just basically synthesized or engineered to to basically get the job done as effectively as possible. All right. I can imagine a supercomputer center would use a lot of these products because they have to make sure that they can cool down, all their components, effectively.
They'd apply it with a mop.
Sprayer, hose it down. All right. All right. So next, so we have talked about almost all of the important components. RAM is not that exciting. I can show you what RAM looks like, but it's not very exciting, and you just make sure the specs, work out with the motherboard that you're using. So we're looking at desktop memory. If you have a laptop computer and you want to expand the memory on the laptop computer, you can also look up your laptop memory. But as several people pointed out, some brands of laptop computers may use special memory modules that are vendor specific. Okay, so I think Newegg may or may not carry the very vendor specific ones. But let's look at the desktop type. And I think we also kind of talked about capacity. Okay, so let's take a look at these, all these capacity. So even when you look at a fairly typical number, which is 8 gigabytes, you can see there are different types of 8 gigabyte, 8 GB configurations. This is just 8 GB. This is 8 GB 2x4, and this is 8 GB 4x2. So this one is basically one card or one module gives you the capacity of 8 gigabytes. The next one, if you look up the number, this is the most common one, is to use 2 memory modules to give you 8 gigabytes. And then the third one uses up 4 memory modules to give you 8 gigabytes. So this has to do with how many slots on the motherboard do you want to use up just to make it so that it has 8 gigabytes overall speaking. You can also tell just from the numbers or the frequency here the 2 by 4 gigabytes is the most common one. And that's because some motherboards only give you 2 memory slots to begin with, the smaller ones. Okay, so you cannot have 4. The second reason is if you only use up 2 out of 4 slots, that gives you the possibility of expanding that in the near future. Okay. Are there any questions so far? How many people have tried to upgrade the memory of your computer just by adding more memory modules? Okay, did it work out okay?
Oh yeah, yeah. Done before. I started out with the system I bought and came with 2 gigabyte modules.
Mm-hmm.
To check the specs on it. Went shopping.
Mm-hmm.
Found the brand I like, and with the latency, it doesn't really. I don't notice a difference, but it runs very smooth and stable.
Okay, nice.
Yeah, I had some RAM sitting around, and my friend wanted me to upgrade his laptop,
Mm-hmm.
and it had 2 extra slots in it.
Mm-hmm.
However, what was in it already was it had 2 gigabytes, and apparently I put in the other 2 and it wouldn't post
Mm-hmm.
because the motherboard on it actually only had a cap of 4 gigabytes.
Yeah, that's
an issue.
really annoying. Okay, you talked about that one term that I have not explained to the class, POST, post. Okay, so what is special about post? Well, POST actually is an acronym. Okay, it stands for. Let me look it up.
Tell you.
Well, let's look for mother or BIOS. You know that. How to POST is power on self test. Okay, that's what POST is. How big? Well, since I don't really turn off my computer almost ever, so I don't really experience this, very frequently. When you turn on a regular PC, do you guys notice a beep or several beeps when you turn on the computer? Those beeps actually have special meanings. Okay, they are actually the output of post. In other words, if the BIOS figures out there's a problem, sometimes it will use the beeps to tell you what the problem is. Okay? And that's because it is possible that the BIOS could not even get to the video card output before a problem is detected. So it cannot just show you a screen and say, oh, we got into problems like this, because it may not even get a chance to get that far. But a speaker on the motherboard is a relatively simple and always there type of device. So it can always use a beeper, or what we call a piezo buzzer. You can always use that to indicate, hey, there's a problem by beeping how many times and also the frequency. And that's why on some motherboards they also have a little display that displays a number. It's called a post number, code, POST code. And that's also extremely useful, especially for people who want to overclock or do other things to tune their components, because the motherboard may not be able to get very far, but at least when it shows you that code, it tells you how far it got. Then you can do some adjustments accordingly to try to optimize the performance of your computer. Okay, so this is just an explanation to basically explain what post is. Okay. So when you said it would not even post, that means it could not get past post to get into the BIOS actual on-screen display stage.
Yeah, it was a laptop. I turn it on, it would just be black.
Mm-hmm.
Just nothing. And I figured out it was the RAM because I put in just a single 4 gigabyte. It worked fine. I put in mine separately, and it's just the combination. Once it hit over 4 gigabytes, it just wouldn't do anything.
Yeah, sometimes how you put it in, like which one goes with which other one. The pairing is also important. I think you pointed that out, like maybe last class or the class before last. You also have to keep in mind, some older computers have a maximum in terms of how much RAM you can address. So some would not even post. Some will post, but it will not make use of any additional RAM. My wife has an old Toshiba computer, and we just thought of we'll just add more RAM to it so it can run Photoshop and some other RAM hungry type of application. It will not accept any more than 3 gigabytes, which is a really odd number. So we bought 4 gigabytes for it, and out of the 4, only 3 could be used. So the last gigabytes basically was just pointless, which really kind of upset me because I also bought Windows 64-bit just for that. All right. So if you want to look up, post because your computer would not start up, these would be good articles to read. Okay, if you ever encounter a situation where you power up a computer, you can tell some of the LEDs in the inside of the lights are kind of lighting up, but the computer is not turning on, your hard drive is not spinning, there's nothing on the screen. Reading some of these articles can be helpful because by the pattern of it beeping, or not even beeping at all, that might give you some idea of what may be wrong with your computer already. All right. So memory, we look up 8 2x4 gigabytes because that's really the most common configuration. If you just look at the frequency or the offering of each type of memory product, you can see that this one has 222, which is almost doubling the second one, which is 16 gigabytes 2x8. So let's take a look at this one, and we'll still sort by best rating. And you can see that you pay about $63 for 8 gigabytes of RAM, and that's that's the current price of DDR3 memory, which is not really a lot of money. You buy a computer for several $100s, and getting it enough RAM can really make a difference. Sometimes it's really difficult for me to see people spending hundreds of dollars on a computer, and then they just kind of cheap out on the most important components that are inexpensive to begin with. The processor, not so inexpensive, okay? But RAM, bumping from 4 gigabytes to 8 gigabytes is just 30-something dollars, okay? But it can dramatically improve the performance of a computer. So that's one thing that you can look into if you have an older computer or some computer that you put together or purchased in the past 2 years or so. It has 4 gigs of RAM and it's becoming slow. Adding memory can be one of the factors that can help make it faster again.
Why did that? It used to be that was really expensive, double the amount. Why did it get so cheap?
It's just semiconductor. Remember what we said. Manufacturing process has improved or refined for one thing. Transistor size getting smaller. Is also one major factor, because let's think about the whole process of making semiconductor products and why having smaller transistors can help in almost every respect of the business of the industry. Okay, so where is this picture? By the way, I was thinking about getting a live scribe pen. Does everybody know what is a live scribe, computerized pen? Okay, go ahead.
Is it one of those pens where it writes, where it records your pen strokes?
Yes.
And then digitizes them so you can turn the text into an actual word processor?
Correct. It's basically a computerized digitizing pen. I do not own any stock in this company that I know of. Okay, my mutual funds, some may have a investment in a company like this, but basically it's a computerized pen. It writes just like one, and you have to write it on special paper with special dot patterns. But basically, what it does is it can record what you write. Okay. In other words, you have to buy the special paper to write something on it so that it can be digitized. But once it is digitized, it is either stored on the pen itself, or in this case, it has Wi-Fi. It can actually go up to the internet by itself to store all that stuff online. It also has a microphone on it too. So in a class situation like this, when you're taking notes, you can turn on the microphone to record what I'm saying, and you can write your note at the same time. After the class or with a Wi-Fi connection, even during the class, okay, you can lose your paper. Okay, whatever you write it on, the actual physical paper, you can toss it away, recycle it, burn it up, whatever. And the content is already either stored on the pen itself, or in this case, uploaded to a website. Yep.
I had an older one when I was in high school. It didn't have the Wi-Fi or anything, but I was never able to use it because it was too loud in the classrooms to record.
Oh, okay, so it would not record correctly.
Yeah, it'd pick up too much, like
background noise.
People talking and the air conditioner and all that.
Someone actually tried this out in one of my other classes last year, and it was able to pick up my voice fairly well. I guess in a classroom like this, the noise is not as much, and it it could pick up enough that the student was able to use it for studying purposes. Okay?
I had one previously, and it was older. It didn't have the Wi-Fi and all that, but it has a bunch of other really cool features, like it definitely identified and associated the point at which something was recorded and when you wrote something down.
Right.
So if you were just taking notes on a lecture and just writing down keywords, you would hear the whole phrase that, let's say, the professor said by clicking underneath that word. And
Right.
it had a program in it where you could draw like a piano.
Yeah.
And
It
then play.
basically can sync it. It's basically the computer. It's a computer in the shape of a pen and pretending to be a pen. Okay, but being a pen is the last thing that it is. It's basically a computer with a sophisticated camera that picks up the dot pattern that your bare eyes cannot see on the paper. Okay, so you have to spend money on the pads because the writing pads are special. They have special dots on it, and I think the new ones can even tell which page it's on. So when you write it on a different sheet of paper, when you go online, you can actually say, okay, what is page 20 of the notes that I told today, and it can actually go to page 20. You can also play it live too, quote unquote. You can play it in. You can replay, okay? You can replay the note-taking process. So you can click a button, and it will basically you can see on screen, the way you actually wrote, and with the voice replaying at the same time. Okay, and this is basically the state of technology. And the new one, the Sky is Wi-Fi capable. So if you have a place where there's a hotspot, or your phone is capable of Wi-Fi hotspotting, you can actually have this thing to live cast, the recording, the voice part, and also the writing part at the same time, which is kind of interesting. Okay, it's really useful for classes like art classes, or maybe physics classes or chemistry classes, where a lot of stuff has to be written, on a piece of paper, traditionally, and now a professor can do it on a piece of paper, maybe on the podium, and the projector can basically, it can be projected on the screen, exactly the way things were drawn or handwritten, and everything can be uploaded with a record online. Yep, it's not cheap. We're talking about $200 for $200+ for the high-end one for the Sky, and maybe 100 something, close to $200 for the lower end one. But just being able to do that, technologically speaking, that part is still amazing. Just being able to fit all that computation power into a pen-like object and have Wi-Fi capability at the same time, that really is technology at work. I'm not planning on getting one because it has no Linux support. All right, so let's take a look at a picture of one of these, just so I can give you an idea of the components and just general ideas of how to use one. How do we use a RAM module? How hard can that be? All right, so let's take a look at a picture of a single module. It's called a DIMM, D-I-M-M, which stands for Dual Inline Memory Module. Okay, the dual part applies to having pins on both sides. Let me just do a magnification here so I can tell you what I'm referring to. There we go. So if you look at these things here, the little metallic parts, each one is called a pin, okay? And dual inline means it has pins on both sides of the surface, okay? Single inline, which I guess was an older, much older standard, only has pins on one side. So dual inline is the de facto standard. You cannot find single inline anymore. Memory module, that doesn't require any explanation. Let's zoom out again. And you can see that there's a notch here, right? There's a little notch here. What do you think that notch is for? So the things cannot be plugged in backwards. You give consumers a chance to plug something backwards, and someone will figure out how to plug it backwards. You put in a notch like this, someone will still try to plug it backwards. Okay, but this notch is basically what it's for. It makes it asymmetric. In other words, you can only plug it into the motherboard one way, but not the other way. Okay, I have known people who plug in these memory modules, using the wrong orientation and have the whole thing lopsided because only one part can fit in at any particular time. Power up the computer, it's gone. So you gotta really observe these things. On the motherboard, there are designated slots to push these things in, and they have two plastic levers on the side. When you eject it, you just push the levers on the side, the right one further to the right, the left one further to the left, and it will pop up the memory module that is already installed. When you install a memory module, you just plug it in straight down until you hear a click, and the two levers will close and snap in place when you install a module like this. So in other words, I think a regular consumer, just by observing how to do something like that, or watching YouTube to learn the basics of how to do it, can replace the memory modules without a whole lot of problems. How many people have done that? See, there we go. When I said done that, I mean installing memory modules correctly and not slanted sideways backwards and otherwise causing problems. All right, so memory modules, not very exciting. We talked about motherboards already. So what do you do to put everything together? Fish tank and transformer oil. Well, that's one option. Yeah. You had something to say?
I was just going to say that Moore's law is really, really, I always see it the most with the RAM memory. Because I remember first learning how to do plug and play, putting it in, and it was at like 125 megabytes, not the 256, not the 512. Now we're at like 8 gigabytes for one slot.
When you look at the actual bus speed, like how much memory you can transfer between the processor and memory, now with an i7 processor that's costing about $300, the transfer rate is 5 gigabytes per second, which is a lot. That's 5 billion bytes per second that can transfer between the processor and memory.
Yeah, RAM available today comes with usually the heat shields, which I know as far as even 10 years ago, then maybe about half of the products came with heat shields. So again, even with our memory modules, then heat is a culprit of sorts. Enough to
can be because it's switching really fast. It's the switching that is generating the heat. Yep.
Going back to the Titan, did you see how much memory that had?
Let's go back there.
You still have it up there?
Yeah, where is it? Titan right
Look
there.
how much memory it has.
Memory is 710 terabytes. Okay, so for those of you who are super gamers, you can probably install up to 32 gigabytes of RAM on the motherboard, and that's the limit. It's the limit not of the motherboard, but of your processor. Okay, if you look up the i7 processor,
It's up to 64 now, actually.
up to 64? Okay, well, big deal, we're doubling it, right? Okay, so how does 64 gigabytes compared to 1 terabyte? 1 terabyte, okay? All right, so 1 tera, okay, 1 giga is 1 billion, okay? So 1 billion is 1 giga, okay? 1 tera is 1 trillion, okay? So 1T is basically this number times 1,000, okay? So there are about 16 or so 64 gigabytes, which is the maximum you can put on a consumer motherboard in 1 terabyte. And this thing has 710 terabytes of memory, which is a lot, okay? Which is also what you need in order to do simulation, because in simulation, you're basically looking at the interaction of one tiny little particle and how it interacts with another tiny little particle. And there are lots and lots and lots of these tiny little particles. And that's why you need the memory in order to represent all the particles that are being simulated. And, but it's interesting. Space, just look at the space. It's not really that much. It really is not that much. It has 43, about, let's call it 4,000 square feet, okay? 4,000 square feet as a facility, it's not that big, okay? I know people with houses up to 5,000 square feet, okay? So it's not really that much space. And if you look at old pictures of IBM mainframe computers, Those things take up a lot more than this much space. It takes up a whole floor of a big building. Those older computer centers. So this is not really that big, site-wise, and it has to get rid of 8.2 megawatts out of this kind of surface space. And that's a lot. What is your electrical bill? How many kilowatts do you think your house is consuming, even when you have your electric heaters turned on for the entire house? Now, one heater is about 1.5 kilowatts. So how many of those do you need in the winter in order to heat up the entire house to a temperature that's toasty and comfortable? Just a guesstimate. 500? No, you don't need that many to heat up a house. I mean, one 1.5 or 2 kilowatt space heater is probably good for a 12 by 12 room. So we're talking about 144 square feet or so. So when you have 5,000, so let's do quick math here. So 5,000 square feet divided by 144 square feet, I would call that approximately 30. Okay, we'll just call it 30. And each room requires maybe 2 kilowatts. So we are looking at 60 kilowatts of power in order to heat up a house, from a, in the winter, from a cold, kind of like not so comfortable temperature to a toasty temperature. This is a realistic number, okay? And now we have, a space about the same, 4.3, thousand square feet, but with a power going in, which is rated at 8.2 megawatts. So what are we talking about here? Yes, way more. We are talking about more than 1,000 more thermal power going into the same area. Okay? So being in Alaska is not going to be very helpful. It helps a little bit, but not nearly enough. Okay? So is that kind of give you guys a sense of what kind of power we are talking about here and why heat extraction is a problem? Being very deep in the ocean helps a little bit because water is really cold when it's at a very deep depth. Because ice is 0 degrees Celsius at 1 atm or 1 atmospheric pressure, but under a lot of pressure, the freezing point is much lower. In other words, water can stay in a liquid form at a much lower temperature when you have a lot of pressure, like from other water on top of it. So that may be the next place to put a superpower, super computing center. It's like really down there, because liquid is also good at getting rid of heat too. Yep.
Put it in space.
Huh?
Just put it in space.
Space is actually not a good place because in space you can only get rid of heat by radiation, which is actually the worst way of getting rid of heat. Okay, what is radiation versus cooling by air and versus cooling by liquid? Okay, how would you rank those three? Radiation is the worst because radiation is just laying something in vacuum and just waiting for all the heat to radiate away. Now, outer space is extremely cold. Yes, I can definitely understand that. But at the same time, radiating heat is also a very slow way of getting rid of heat. And that's actually why, in sci-fi, in Star Wars and stuff like that, you see all those, kind of energy beam type of weapon, firing all day long and continuously. It cannot be, it's not possible using our existing technology, because they found that, the limiting factor of those, energy beam weapon is the same thing with a supercomputing center. How do you get rid of all that heat? Because if a high power laser fires, it generates a lot of heat, it will heat itself up. In outer space, you can only wait until it radiates all the heat away, then you can fire again. And as it turns out, it takes an extremely long time to do that. Now, in atmosphere, it takes less time because you can have all the fins and air cooling to help it cool down, and it's still ineffective. And that's why we don't have energy weapons, because it's not a very effective way of doing things. In fact, I know we're running out of time here. Yep.
I'm just going to be that nerd and deviate just a little bit. in Star Wars, they actually do explain how they can continue firing the energy blasts. That was actually explained.
Aha.
There's like this cryogenic chemical that they actually funnel through the entire ship.
Then you can then you run out of material eventually because all that material is going to be.
It's supposedly
It's
very
expelled.
efficient in terms of like how it's able to do it, and there is limits to how much it works. But
Say whatever they want.
I'm just saying.